All right, so the lab session is being recorded now. I'll just give a small restart to whatever I said. So I'm Palash Agrawal, and I'm going to be your TA for this course. And welcome to a series of, I'd say, 7 lab sessions on deep learning, where we're going to be learning various practical aspects of deep learning. Uh, So if you go to, let's say, the course website and look at the lab sessions, you're going to be seeing that these are all the lab sessions. There is one prerequisite to this lab session, which is for those people who think they're not as strong in Python. So I've pre-recorded this video and I've put up the link to the notebook. Uh, go to it and make sure that you watch this video if you're unsure about your skills in Python. But if you are confident in Python, it's totally optional. And so let me walk you through some of the logistics for this lab session. Uh, and So this lab session is going to be a very practical introduction towards, like building your models in deep learning, apart from the theoretical aspects that you're going to be studying within the lectures, the lectures that Kamlesh sir is taking. And we're going to be looking at very modern, very hands-on 2022 stuff, not stuff from 1990s and stuff like that. And we're going to be looking at like various aspects, like how do you build your models, how do you design your components, how do you build your pipeline, how do you resolve errors when you're building models. And so I think the best way to do that would be sort of a live coding session in which I'm going to be coding and you guys would be following me along. So let's actually get started with it and slowly we'll get acquainted with stuff. So I'm going to be creating a new Google Collab notebook. It's a platform where we're going to be building a model. So you go to your drive folder and you go to plus new at the very left. Go to more and then press Google Collab. There you go. And it's gonna open a new notebook, and the notebook is gonna come over here. Okay, never mind. It's loading. I'm gonna be sharing this notebook on the chat so you guys can open it and then you can, you know, like in case you fall behind, you can just go back to the notebook and then you can follow things back along. All right, let me share. Okay, so first of all, I'm just gonna name this, let's say, lab 1. All right, and this lab is gonna be upon some basic introduction to the machine learning, not necessarily deep learning, but then the machine learning fundamentals that you require in order to build your models. One thing, if you guys have any doubt, feel free to just open your mic. I may or may not have my like the Google Meet screen in front of me, so I may not be able to read my messages. But if you want to ask me anything, you can simply open your mic and stop me, and I'll try my best. All right, I'll share this notebook with you. All right, I'm sharing this notebook on the drive. All right, so let's get started. So so what exactly is this platform, this Google Colab? I've explained this in my Python introduction to Python video. So please have a look at it if you're unfamiliar with any of this setup or like Python in general, or like if you want to get a very basic introduction towards what deep learning is in practice. Like in that session, I've also built a deep learning model from scratch with with very few lines of code. So it'll give you a very good idea about like how deep learning looks like and how interesting it is. So this lab session will be on ML models, and how do you deploy your models as well, which means that like you've built your models, but then you also want to like build an app out of it, like an application, web application. So we're going to learn how to do that as well. Very interesting class. These lab sessions are going to be about, let's say, 2 hours. Today's lab session might go slightly beyond it because I'm trying to you know, I'm trying to give introductions as well, and I'm assuming that most of you will have some issues, catching up. So I'll try to go a little bit slow. If you guys feel I'm going slightly fast, stop me. Feel free to stop me. All right, so I hope you guys have made your own Google Colab notebooks. And so so we're not going to look at all sorts of machine learning models. We're going to look at machine learning models that actually matter for for deep learning, which are linear models, right? So what are linear models? So we're gonna look at specifically we're gonna look at two types of linear models. We're gonna look at a linear regression model. I'm gonna look at a linear classifier. And to be fair, these are not two very different concepts, and which is why I've clubbed them all together into one model, which is called linear model as well. So of course, I'm sure you guys know what linear models are, at least in mathematics. So let's say a line's equation is y is equal to mx plus c. That's a linear model. And then how do you use it in, let's say, machine learning? And so the point of linear models is to take in, let's say, various um, let's say data points as the input, which is x within this y is equal to mx plus c equation, all right? And then our task is to find, and then there is a corresponding y as well. Now we have x's and we have y's, but we don't know m and c, and we would like to know this m and c because we want to know the relation between this x and this y. Why do you want to know this relation? Because you don't have data for every you don't have data for every instance in this world. And let's say whenever there will be some instances in which you don't know the y, you would like to know the y, but you have the x, right? And in that case, this M and C, which we've learned through examples from the past, is going to come in handy, and we're going to be predicting a y. So enough of this math jargon. Let's actually take a very real life example. Now let's say you're in the stock market, all right? And the stock market, let's say Google stock. Let's look at, yeah, here's the Google stock, and let's actually zoom out, and you'll see that there's a trend that it's slowly going upwards, all right? So I mean, let's say you would like to predict what will be the price of this model, let's say next year, which is 2023, January 1st of 2023. And you would imagine that it's um, that it will only increase, but let's say for all you know, it can decrease as well. But you would like to predict the model based on whatever data you have, which is the data till now, till January of 22nd, 2022. Right? And that is essentially is machine learning, right? Which is identifying patterns within whatever data you have to predict uh, to identify patterns within data in order to predict, in order to classify, in order to generate stuff like that. All right, so um, we know that in 2007, let's say on 10th of November 2006, the price was $236. Now, on 29th October 2021, the price is about $3,000, let's say, and there's a whole range that goes up. And you can see a trend that it's constantly increasing, right? So you would like to build a model that best fits these data points, right? And that is done using these mathematical models, like so it can be any sort of model, it can be any wiggly model, let's say, per se. However, why linear models? It's because they're the simplest of all models, right? They're the simplest model possible. Uh, yeah, which is a simple y is equal to mx plus c. Or if you can extend it into, like, let's say, more dimensions, and then it becomes y is equal to m1x1 plus m2x2 plus m3x3 and so on and so on plus 4. So this is a simple equation of a linear line, right? Like, which is uh, mx plus c, right? Assuming that x is just one dimension. But then here's the problem: in machine learning, we actually consider or in deep learning. Like, so when I say machine learning, it also implies to deep learning, because deep learning is nothing but a small, like, sub part of machine learning. Let's say in machine learning, we don't. Whenever we have multiple types of features, let's say, for example, over here, there is only one feature, which is the time, right? Which is, let's say, on this date, the price was this. But let's say there were other factors as well, let's say, which says that on this date, in this country, uh, the price was, let's say, different. So time and then country becomes two different features, and they're considered independent. And machine learning, they now mathematically they are completely independent, and so you have to let's say model this in this way, which is m1 times x1 plus m2 times x2, and then maybe some others as well, and then finally a constant, right? So this is nothing but the basic equation of a linear model. And so now I'm going to define like what exactly are we going to be doing. So we're going to be looking at two types of problems, which is a regression and a classification. And I'll later show you a unification that these two are not completely different. They're in fact one and the same thing. And the difference lies in only one very small component within our machine learning model. But regression is nothing but predicting a certain value, right, in machine learning. Now, regression in statistical theory means just to find the relation. So if you simply solve this equation, if you have x, you have y, and then you have x. If you simply find m1, m2, and c, you've done a regression. You've completed a regression problem. So in statistical theory, just to find the relation between x's and y's is called regression. But in machine learning theory, in machine learning, regression almost always means to predict a certain value. I mean, obviously, to predict a certain value, you would first have to identify these m1, m2, and c, which is you have to find the relation between x and y. And so it's not completely, let's say, like a wrong representation of the word. It simply means that you would simply identify these m1 and m2 and c based on whatever data you have, so that whenever you put a new x, which is, let's say, 2023 or 2024, right, a certain date in the future, you get a new value, which is a good indicator of a prediction of what that model is going to look like. So what the value is going to look like into the future, or for any data that you've not seen. You can use it for any sort of things, like like predicting the rent of a house given certain factors in an area, or to COVID prediction, let's say, for example, and stuff like that. So today we're going to be looking at the stock market example. It's a very famous problem, and we're going to be taking our data from a website known as Kaggle, right? And Kaggle.com. So please log into Kaggle.com. You simply go to Kaggle.com, and if you've never used it, you simply go and register using your Google account. I would recommend using a personal account or your BITS email account, doesn't matter. Go to Kaggle.com, and we'll actually first have to set up Kaggle before we can take any sort of data. All right. So my main task is to predict the price of a stock few years down the line. All right. All right. So what you need to do right now is that when you go to Kaggle, on the very top right, you'll see your icon, right? In which you go to account. All right. So I'll wait for you guys to do that. I'll wait for probably 15 seconds. All right. So on the top right, you'll see your icon. You go to account. All right. And then over here, when you scroll down, you'll find this thing known as API. All right, which means that you'll be using a sort of software which connects Google Collab to the servers of Kaggle.com, so that you can directly download the data from there. Right. For that, you need an API. Now, why can't you directly download? Because it's open source. You cannot, because you actually need an API token to do that. And what it essentially does is it sends Kaggle information about you that you, so for example, me, Palash Agrawal, who's located in this location, is trying to use this data. Now, this is important for Kaggle because some of the data sets, they have some legal implications. So they have to keep a record for this. Like some of them are confidential, some of them are, like only restricted to certain people. So they have to take care of all these legal stuff, but we don't have to worry about it. What I'm going to do is I'm just going to simply uh, press create a new API token, and it's going to simply download uh, uh, a file known as kaggle.json. Now, make sure the name is kaggle.json and nothing else, right? And all right, back on my Google Colab, I'm gonna start typing, and I'm gonna go and say that from google.colab import file. So I need to first upload this kaggle.json API onto my Google Colab. So for that, I'm gonna have to write certain code. So whenever you want to upload any file, you need to use an internal library, which is google.colab. And then I'm gonna say uploaded is equal to files.upload, which is gonna create, let's say, an object in order to let's say download anything. And let's run this. So it's for the first time okay. For any of you persons, if you don't know how to run anything, you type something inside this code box, and then you pressed shift plus enter in order to run that cell. Now you can also like press the little triangle on the left side, but it's very slow. You wouldn't want to do that. The best way is to press shift plus enter, so it's gonna run that code and it's gonna come to the next cell. And then you can use your mouse to go back to any cell again and do whatever you want. If you don't know how this works, please go look at the Python introduction to Python video. So it's gonna give you an option that looks like that says choose files. I'm gonna press choose files and go to the location where you have that file, and make sure that you upload kaggle.json file. Now make sure that the name is kaggle.json itself and it's not kaggle.json1, like in case you've downloaded it multiple times. Are you guys following me?
Oh, I'm getting a module not found error.
You're getting a what?
A module not found error.
Where?
So like when I press shift enter after the files function, that's what I got.
Module not found.
Yeah.
Um, let's look at it. So here's a very important skills that you all should learn, which is Googling your errors. Import files, module not found. Let's look at it. Are you getting? Mhm. Can you? Okay, so here's something really good. Are you sure that you've written this line of code correctly from google.colab import files?
Yeah, it says that there's no module named google.collab.
All right. So sometimes
I think
Google Colab.
I read in collab. Yeah. Okay, sorry. Yeah.
All right. Mostly it's usually an error from our end, but let's say that if you think that the error is not from your end, the best way to is actually restart the entire notebook, because sometimes there is an error in loading certain stuff from the Google servers themselves. So it usually works fine after that. Anyways, once you've downloaded that, now here's a kaggle.json actually expects you to store the Google kaggle.json file in a very particular location. So wherever you're storing this. So for example, we are running this on a Google server, and Google server is running this on a particular computer, which is a Linux-based system, and it expects that file to be located in a very particular location in that computer itself. So which is in fact the root folder, and in a very particular folder within the root folder, which is .kaggle. So we're going to make that. So what I need to do is type in exclamation mark, and what exclamation mark does is that it tells Google Colab that it's not a Python code that you're trying to write, but it's a Linux code. So it's gonna run directly on the Linux shell on which the Google Colab is run. So you're gonna be doing, you're gonna make a directory which is mkdir, and I'm gonna put a name to it. I'm gonna do a tilde, which stands for root. So for now, just follow me, and I'm gonna create a folder which is .kaggle. And once I'm done that, I'm gonna move this kaggle.json file into this folder that I've just created, which is .kaggle. All right. Yeah, that's done. All right. And now what I'm gonna do is that I'm gonna directly download the one data set over here, which is the Nyse data set, which is New York Stock Exchange data set. All right, and there's one particular data set that I'm trying to look for. Um, yeah, I think yeah, this is the data set that I'm trying to look for. So um, I'm gonna put this link on the Google Meet for you guys to go and look at it. So either you can directly download a zip folder from here, but the best way is to actually directly download it through the cloud server itself. So it's very, very fast that way. So the command to do that is so you can actually find that command over here actually. Go down and then you'll see I don't want to download it directly. No. Um, where is the copy API command? You can either go over here, you can directly paste it, but make sure that it's a Kaggle command because this is not a Python command. It's actually Kaggle is the API that we've worked on is actually a Linux command, so you directly download it on the Linux server itself. So it looks, which is Kaggle datasets download d, and then this is the username and this is the name of the dataset wherever it is. So this person must have uploaded this dataset on Kaggle. I'm going to be running this, and it downloads it. And look at it; it's about 30 MB over here. So that's about 30 MB, I'd say, the dataset. That's good. All right. And so if you look at like what exactly is in our directory over here, you'll see, and which is done by a Linux command, which is ls. So type exclamation mark ls. You're gonna see there's a file known as nyse.zip. So it's a zip folder. So you need to unzip it, which is again an Linux command which goes unzip, and I'm simply gonna go nyse.zip, whatever the name of the file, and it's gonna do that again. Now go back to the ls command again, what you've written, and run it. Best thing about Google Colab is that you can just simply change the orders of the commands. It doesn't matter. Like you can run something at the top and then at the bottom and then come in the middle, and the order remains in the same way in which you've run it. All right. So you can see that there are many CSV files, which are nothing but Excel type files, like fundamentals.csv, prices.csv, securities.csv. Now there are multiple things, but I think we're only concerned with one of the files, which is this price split adjusted.csv. And if you want to look at like what each file corresponds to, simply go onto that Kaggle page and like read the description of the challenge itself. I'm going to be using now. Whenever you have CSV files, you will almost always be using this library known as pandas, which is very good at handling CSV files as data frames. So data frames is like a table of data. And so you're very helpful in, handling data which is of multiple dimensions, I'd say, right? And you're gonna look like what it looks like. So you're gonna be doing import pandas as PD, which means that I'm gonna be giving a nickname to pandas because I'm very lazy to type pandas again and again. So I'm just gonna say PD, and Python is gonna understand that I'm referring to pandas. Data frame is equal to pd dot read CSV, because I'm reading CSVs, and then the name of the file, whatever is over here. So I'm gonna say price split adjusted.csv. Now make sure um, your underscores are over there, and sorry, your dashes are not underscores, and the name has to be very exact, right? Make sure of that. And now, if you look at if you type data frame.head simply, right, which data now dot head basically prints the first 5 lines of the data frame. And so you can look at this. It's going to be so these are row number 0, row number 1, row number 2, row number 3, row number 4. There's date. There is a symbol which is WLTW. I don't know what that is, so let's look at it. WLTW, which is Willis Tower Watson. Must be it's a New York Stock Exchange company for now. All right. And then on this date, the opening price was this, the closing price was this. Of course, this is in dollars. The lowest price was this, the highest price was this, and the volume of trade was this. That's what uh, is there. Now, all of these date, symbol, sorry, not symbol. Symbol is just the identification for us. Like, if you wanna just predict the price of, let's say, Google, you would simply filter out the rows in which the symbol name is Google or whatever the corresponding name is. And then you can use date and the opening value and the closing value and the low value and the high value to identify the relation between, let's say, oh no, I mean, one of these has to be the price of the volume. So I'd say, well, let's say the opening price is a good indicator of the price on a particular date. Like, because in a particular day as well, the price fluctuates a lot. So let's just take one value, let's say opening value. And you can use, so over here, we have just one indicator of, let's say, the opening price. Now, for me, closing, low, high is of no value. Probably date is of some value and volume is of some value as well, because it helps predicting like what will be the price of, helps identifying the trend, right? Like, if the volume is consistently high, volume of trade, you can expect that the stock is going to do well. But for simplicity's sake, I'm just going to use one variable over here, which is date. All right. So I'm just going to be modeling this value of the stock, which is y in my equation, in terms of the date on which the price was so, which is my x. And I'm going to be modeling the equation as y is equal to mx plus c. My job is to find that m and c. I don't know that m and c, right? Which is, in fact, which is the entire crux of machine learning, which is you either have two ways to find mathematical relations, which is you don't know y, but you know m, x, and c, so you can find y, right? Which is how you build, which is basically all of software engineering, so to say, that you given some input, you know how to calculate the output, and you give the output. Now, let's say you don't know the method to calculate the output, but you know the input and the output. So our task is to reverse engineer the task and to find the relation between x and y, to find how to find the relation between x and y. That is machine learning in its all glory. That's the basic understanding of, that is what machine learning is, in fact. And that is what deep learning is. Now dates in this are nothing but strings, right? And I so I'll have to first process this string, because for Python doesn't know that this corresponds to a particular date, and it doesn't know that, let's say, this and this are one day apart. Python doesn't know that. So Python, we'll have to give it a mechanism to understand that these are dates, and these can be modeled as mathematical values inside this y is equal to mx plus c. Of course, now in y is equal to mx plus c, computers don't understand strings. Like x has to be a number, because that's what computers understand. Computers essentially understand numbers. If you want to do any sort of mathematical calculation, you'll have to convert them into some sort of mathematical expression. And so strings won't work simply like that. So pandas actually gives us a very convenient way to do that, which is known as parse dates, in the sense that we can identify the string, the format of the string, and automatically, parse them, uh, automatically, uh, sort of process those dates as to whatever you need. So this date column will now be used as an object to another library, which is actually going to do the mathematical conversion for us. So just a very small heads up, right? Yeah. All right. Now, since I'm interested only in Google stocks, let's say, I'm gonna I'm gonna simply take out only the rows which correspond to, let's say, symbol corresponding to Google. Let's see what the symbol of Google is. Google stock. So it's known as Google without an E. All right. But sorry. Let's say NYSE symbol. It's not Google actually. It's Goog, GOOG as far as I remember. So I'm gonna look. So I'm gonna tap it into my symbol column. All right. Sorry, symbol column. All right. I'm gonna do uh, Goog. All right. And now I can simply now I don't need my rows to be 0, 1, 2, 3. I can simply take my date as the row value itself. So I'm going to do that using this index set index. I'm going to be passing this. All right. So now let's actually look at the Google data frame dot head, which will be the first 5 values. All right. So here it is. There's a date and there's an opening value, closing value, and whatever. If you want to look at like how many rows you have in total, so we have about 1,762 data points, which we're going to be using to model our data. Now, if you go to the Kaggle page, you'll find that the data is still 2016, I think. Yeah, data from 2010 to 2016. Let's say. So that's 1,762 days. And I'm sure that is it. 102 days in years. Yeah, that's about 4.82. All right, like that must be how many data points we have. Anyways, uh, if you wanna let's say look at one particular data point, all you need to simply do is use the LOC attribute within this class and pass in, let's say, any index over here. Let's 2010 01404, which is 4th of January 2010, and then you're gonna see sorry, Google. Yeah, you're gonna see stuff like this over here. All right. I'm also for better visualization. Let's actually plot all this stuff. So for plotting, we're going to be using this library which is known as matplotlib. So I'm going to be doing matplotlib.pyplot as plt because I'm very lazy and I don't want to type matplotlib.pyplot again and again. Plt.figure, and I'm just creating an object which creates my figure over here. I'm going to set a certain size, which is, let's say, 15,7 works, which is 2:1 ratio. Anything like that works pretty well. I'm going to do plt.plot google.df dot opening or closing value. Let's take closing value. I think closing value is a better indicator of Google df with an underscore. Yeah, and it plots all your data points over here. And you can look at how it has automatically, because we've parsed the dates, it automatically understands that these are dates, and it has not printed strings but rather the dates themselves. So Python understands that. It's very cool. And here's the price of the stock on the y-axis. If you want, you can probably put in like the what do you call markers and legends and stuff like that. But I'm not going to do that. Never mind. So now I want to predict um, approximately. Now the reason I'm saying approximately is because you're going to be fitting. Our task is to actually fit, let's say, a linear line through this model, which is to find M and C such that the line passes the best through all these data points, which you would imagine would look something like this if you can follow my mouse, right? But then, of course, it now the reason I'm saying approximately is because it always won't give you the perfect answer, because of course this is not linear in the first place. And if you're trying to fit a linear model, there will be a trade-off of accuracy, right? So, but your task is to find the best possible answer that you can find using a linear. So if it's close, I'm pretty much happy with it. It's pretty much my answer. So approximately the price of this stock on some date, using whatever data I have, right? So if I um, so and I'm writing this down so that if you decide to go through this notebook, it's a very important line. So if I fit a straight line to this and extrapolate to a few years down the line, I would get an answer that may be a good predictor. That may be a good prediction, let's say. It may or may not be perfect because you never know how the stock performs. So a very good example is that now, if you look at the Google stock actually goes in a sort of exponential ways, especially during the COVID times. So of course, a linear model is going to fail at that point. But let's say till 2019, it was a pretty much linear line, and we're going to take it. And let's look at it. So, anyways, uh, now I need to, like 2010 and 2017, let's say, is probably not a very good way to like parse or to represent the data feature. I think a good way to represent the date would be, let's say, whatever's the very first day on which I have the data point. So that is 4th of January 2010. Now from that day, I'm going to calculate the number of days that have passed for a particular date. So 7th of January 2010 would be, let's say, x is equal to 3 or x is equal to 4, stuff like that. All right. So I'm going to be using that as my data point. So for that, I'm going to first have to find out what's the very first day that I have within my data point. So I'm going to simply take the minimum of the index itself. Let's look at what the first day is. First day is timestamp 2010 1st of January 12 o'clock. 12 o'clock must not have been specified within that, but since we parsed it through a pandas library, pandas automatically does that and assigns it a default. All right, let's look at def. I'm going to be defining a function that calculates the number of days since the passing of the very first day. Calculate first day since, it takes a date and the reference, and just because I want it to be flexible, let's say, I'm gonna give it a default value which is first day over here, but you have the option to give it any other reference date. And I'm simply going to be returning date minus reference. And because you've parsed it as an object of, let's say, the timestamp library, if you want to look at like the definition, like what exactly is this timestamp is actually must be a library which pandas is using internally. If you type dot question mark like or any object, it's going to give you a description about that object itself. So type Okay, it doesn't give much description, but it's an object of the timestamp library. Okay, and you can do mathematical calculations onto that stuff, and it becomes very convenient in that case. Now, date minus reference is gonna do a difference between years, dates, months, and it's also gonna between the time itself, and so you can have the difference in terms of seconds, in terms of minutes, in terms of. But I only want it in terms of days because I don't care about anything else. So I'm just gonna make sure that I type that. So, uh, but here's the problem. Anything that you pass as a date has to be a particular object, and that object, so a very closely related like object from the timestamp library is. Oh no, okay, here's the thing. So timestamp in itself cannot be subtracted, it's just a placeholder, right? There's another library known as datetime. So from datetime, import datetime, type that. And then when you pass a timestamp object to datetime, you can now do calculations onto that. Now here was a part. Yeah, timestamp is nothing but, let's say, a representation of the day, year, month, and the time. So and that gets passed to the datetime library. So anyways, when I now use my library and I pass it, now I have to pass it as a datetime object because uh, you you can't um, pass it simply. And then there's a particular format. So what's the date today? Let's say today is 2022. We're going to be using the American format because these libraries were developed in America. Never mind. And then today is 22nd. All right. And let's see. Let's look at. So it has been 4,401 days since 10th of January, 4th of January 2010 till today's date. So that's how this library works. All right. Um, Now I need to create I need to extract my x's and my y's in order to build my model. So I'm going to be using a list to do that for now. I don't particularly like lists as my data structures, but because they're very memory heavy, like they take a lot of memory. But for now, for this lab session, we're going to be using a list. So all my x's, which will be all the 1,762 data points as the number of days that have passed since a particular day, and my y's are simply going to be the closing values of that. All right, so let's look at what I'm trying to do over here. Map is a Python internal function which applies a particular function to all the values in a given iterable. So google.df.index is going to return, let's say, a list of all the dates. It's going to pass it through this function, calculate distance, and it's going to return a list, which is going to be my x. If you want to look at x, let's look at x, but not all of x. Let's say only the first 10 rows of x. So of course, it would be 0, 1, 2, 3 up to 11. Anyways, y similarly will be nothing but uh, like the values of a particular column, which is dot close. And let's look at first 10 rows as well. So yeah, here you see the price of that stock on those particular days. So it's 312, 310 the other day, 302. It was decreasing at that time. I'm going to make sure that these two things are of the same length, because otherwise it's going to create a problem.
So I have a doubt. Like, what does
Sure.
dot close represent?
Dot close is nothing but the name. Close is the name of the column. So you can either parse it as a string, but in case that your column value is nothing but one single word, you can simply type it without any string parsing. In case there's a space in between, so for example, if the name of this column was closing value with a space in between of them, then in that case I can't type a space over here. Like I can't type close value, because those are two different keywords for Python. But in case it's just one word, you can just simply do a dot close. And it'll return the values of the close, the column whose name is close. Similarly over here, dot index. Dot index is similar to that. Yeah. All right, so let's actually plot these x's and y's, and I expect that they have the same, uh, uh, same structure as before. But I'm also gonna give it labels, so it's gonna be slightly more comprehensive, slightly more comprehensible. PLT dot x label would be days since 4 Jan 2010. All right, let's see. Yeah. So the value goes on from 0 to 2500. I'm assuming that they must have been sorry. Yeah, stock since closing. But I want to look at like what's exactly the length of buyers or Linux. It's 1,762 points. I wonder why the X goes on until 2,500. X. Okay. Ah, I see. We must have taken some validation data as well. Oh no, we haven't. But okay, let's just leave it. I don't exactly know what's the issue. And they should essentially be only 1,762. Hmm. Ah, I see. Okay, I get it. Okay, there must be many days in which there must have not been data points, but the dates go until, let's say, 1st of January 2017, which must be 2,500 days apart from that. So I was under the impression that they must have given consecutive 1,760 data points, but that's not true. Okay, never mind. Here's two ways to find that m and that c within the y is equal to mx plus c equation. Um, there is one method within statistics which is a direct formula that you can apply onto your x and y, and it will automatically return you the m and the c. So let's not use m and c anymore. Let's actually use a more machine learning oriented lingo. So I'm going to be naming it w times x plus b. So what W represents? W is a symbol for weight, the weight that you give to a particular feature. X is a feature, and B will be a bias. Bias is a more general term um, for the let's say the intercept value that you put in, because it helps you like shift the model in a particular direction without actually without affecting the relation between W and X. And Y will be the label or the output. So Y is the ground truth or the label or the output. W is the weight. X is a feature. B is the bias. Now, I'm not going to be writing that formula from scratch because I don't care about that formula either. But I can directly use a library that will do that for me, because I mean, I guess that's a more important skill to learn than just learning the equation itself. So as I told you, this lab session is not going to be just the practical implementation of what we learn in the theory classes. This is completely different from that, and so that is why I encourage all of you to attend all these lab sessions. There will be an assignment based on this as well, so you guys need to do that anyways. But we're going to be learning a lot of practical skills that will be helpful if you want to be a data scientist, including, like all these small. If there's going to be an error, that's fine, because I'm writing all this stuff from scratch, so I don't know what's going to happen. I might make a mistake, and so I'm going to show you like what's the debugging process, and we're going to be, and it's going to be a good learning experience for all of us. I personally don't like rote learning all my equations because it's not going to be handy in life for you. But I'm going to be using a library which was sklearn linear regression. Yeah, this is the and it uses that equation directly right after this. Now, when you go to the page for that, and you'll see that the input, if you look at the examples, inputs are actually lists of lists, and what that internal list corresponds is like a collection of all the features. So over here we just consider one feature, but let's say there were two features, that is date and the country, and let's say volume of trade as well. So we would parse it as one, like a list of three values, and then overall there would be a list that would contain all those lists. So I need to modify that list over here, because otherwise sklearn is going to give me an error. And I'm just going to go I for I and X. Now this type of writing is called list comprehension. It's a very efficient way, not in terms of time or space complexity, but just in terms of like the ease. I'm just gonna print, let's say, modified X, the first 10 values, just to make sure. Yep, it works. All right. I'm going to be creating an object of the linear regression library, and I'm going to fit modified X and Y. So Y, I don't think there's any restriction of Y. Y can simply be.
Could you repeat how you got to know that you have to reshape your array?
Oh, so I went onto the documentation. Now, okay. So let me show you what happens if I just simply pass in X. All right. It's gonna give me an error that says expected a 2D array but got 1D array instead. So if you go to the documentation of this library, and go to the example, you'll see that they've instead passed a 2D, like a list of list, that is a 2D array in Python, like an implementation of 2D arrays. So they've passed a list of lists in which the internal list, which is this 1, 1, and that list corresponding to that, that's a list of all the features that you have. So over here we just have one feature, but nonetheless scikit-learn over here is expecting us to pass in 2D lists. So we need to take care of that. Do you get that now?
Yes, thank you.
Sure. All right. Yeah, it works now. So that's that. And now it's simply going to give me that W and B, which is nothing but MX plus C, which is coefficients. So the coefficient W is actually named as coefficient within scikit-learn. So again, all you need to do is go to the documentation, and you see the coefficient, which is, since they pass 2D data, they'll get two W's, because W1x1 plus W2x2. So they need W1 and W2. So they got 1 and 2, which is W1 and W2. So for that, I need to type coef underscore. And then to get the bias, I need to type in intercept underscore. So that's that. Let's not intercept. All of this, I don't remember how to write all this code. And I recommend all of you, no one to actually memorize how to write all these libraries and stuff. But what you should learn is to like Google it very fast, go to the documentation and figure out how to do it. I didn't even know how to do this stuff till yesterday. I just went to the documentation, and now I do. So I mean, and that's, I think, the most important skill that you can learn whenever you go to corporate or you go to research, wherever you go. Let's actually look at what W and B will be. Yep. So now I have 0.22 as my what do you call W, and and 172 as my output. Let's actually try plotting this stuff. So now I have W and B. I can directly now fit it onto the model. So now what I'm expecting to do is that I have X's, and I'm going to be passing. So I'm going to be passing X to my WX plus B equation, and I'm going to get a Y corresponding to that. And let's see how close that predicted Y, which my model predicts, is going to be to the original data. Right? Let's look at that. So I'm going to be create a function which is going to calculate Y when it's given an X. So it's simply going to do return X times W plus B. All right, that's it. All right, so I'm going to be now plotting my X's and Y's. And I'm going to be plotting my X's within the same plot itself, and my linear model of O for O in X. Again, list comprehensions, very, very effective. So for O in X, which is these 1,762 values, not this, but this, is going to pass in that through my linear model, which is going to calculate Wx plus B, and it's going to return a list corresponding to that. All right. And I'm going to be copy pasting that label stuff because I don't want to type it again. And here you go. Look at it. It's very, very, it's close. That's the best a linear model can do. Right? A linear model can't do better than this, I'd say. And it was calculated using some direct equation. I don't know what that equation is, and I don't care as far as my practicals are concerned. Of course, you need to care for your in your theory classes if it's taught. But here's how it predicts, and it's pretty good. And so, which means that if I have to predict, let's say I have data till 2017, and if I want to predict for, like, let's say 2018, I can simply extrapolate this line and the corresponding Y. So wherever that X lies, that is 2018, whatever the corresponding Y of this line is going to be a good indicator of what the actual data is going to look like. Because I don't know, I don't have the actual data, because either I don't have the data or it's into the future, so I simply don't know that. But the linear model is going to be a good indicator of what that might look like. So we've just done a prediction model, a stop prediction model. So you want to look at, let's say, days, let's say a particular date from 2018, I'd say 31st January 2018. So I'm going to be passing it as an object of the datetime library in the American format. Days elapsed since the first day would be calculate days since and day. Then let's look at what the days elapsed will be. So now this 3283 will be the X to my model for which I have WX, for which I have W and B. So it's going to be simply days elapsed. All right. It's going to give me a price which is $911. So let's actually look at like how close that is. Let's go to Google Stock. My mouse. 2018, 31st January, 28th January, fine. It's about $1,050. I've predicted $911, slightly off, but I mean, that's what my linear model predicts. And it's not very far off. And then you can probably extrapolate it for, let's say, whatever amount of time you want. It'll work well. Now let's look at another method to actually calculate these W and B, which is actually a very important concept, and this concept is known as gradient descent. and it's a very important concept in deep learning overall. We're going to be learning about this in the lab, in the lectures as well. Let's actually look at what gradient descent is. So I'm going to be now. Let's plot a random function. So I'm going to be plotting, let's say, a parabola. So for that, I'm just going to do range 1000. I'm going to create 1000 data points. Which are 0.01 apart. So 1000 data points for 1000. So it would be from -5 to +5. Let's say. Len Z is 1001 data points. Okay. I'm going to define a function that's going to plot the square of a value, because that's what a parabola is. So it's nothing but return x power 2. Now I'm going to be plotting, let's say, my parabola. X dot plot z, which is my x, and then square of all these values within this thing. All right. I'm going to be creating a certain point just to know that we just to indicate that, okay, let's actually see what this looks like. Sorry. Right. Here's my parabola from -5 to 5, and the y goes from 0 to 25. I'm going to be creating a point that says that that's my starting position as of now, right? So point is equal to x plot. I'm going to be defining, let's say, a variable input. I'm going to be, let's say it's 4 for now, right? And I'm going to take in the input, the square of the input, all right? Some bookkeeping. So I want to differentiate. So I'm going to make it a red circle. So that's what I'm doing over here. And I'm going to increase the marker size to 10. All of this doesn't matter. I'm also going to be plotting, like mentioning the position of that dot. So it's a text, but plus 0.5 square, which is just offsetted by 0.5 centimeters. That's what I'm doing. F. So here's the text that I want, which will be up till one decimal point, and of course the square as well, which will be square input up till 1 decimal point. All right. Yep. So there's 4.0 and 16.0 as one of my data points already. So this is my starting point, and this is important because initially you don't know WNB, so you would be starting with some random WNB, and you would expect some mechanism in which you can progressively come to the best value that is possible for WNB. And so this is known as gradient descent, and there is a mechanism that involves gradients or derivatives, which is why it's called gradient. And we'll talk about it. Now here is the concept of gradient descent. Now mathematicians realize that whenever you draw any curve, the minima of that curve can be characterized in terms of the gradient of any point, like of the equation at any point. So for example, if I start at 4, 0, it will always be true that the minima, or at least the local minima, that is this point, x is equal to 0, y is equal to 0, will always be in the opposite direction of the gradient at that point. So if you draw a gradient over here, you would expect, so y is equal to x square's gradient will be 2x, which is 8 at that point, plus 8, plus represents positive values. You always have to take a step in the opposite direction, that is in the negative direction. So you need to go from 4 to 0, which is opposite direction, in order to reach the minimum. And that is in fact the definition of gradients. That is how gradients always gives you how the value. So what is the definition of a gradient? A gradient is nothing but like if you increase, so if you do del y by del x, it simply means that if you increase x by a certain value, small value, how much will y increase? So if you want to reach to the minima, you obviously have to travel in the opposite direction because you're trying to decrease, right? So that's the concept of gradients. Now, if you were to take it in the opposite direction, if you were over here, let's say, you will get a negative gradient, which means you'll have to travel in the positive direction in order to reach the gradient, and it always checks out. Mathematicians identified this. This is not a machine learning specific stuff. So I'm going to be calculating I'm going to defining a function that calculates the gradients. I'm simply return 2 times x because that's the gradient of x squared. I'm going to remove so point over here is nothing but a small list. I'm going to be removing let's say, right, just a second. I'm going to be recursively running this function. All right, x1 remove, and I'll show you how this will progressively work. It'll be fun. So input is equal to input minus 0%. I'm going to take increments of 0.3. If gradient of square input greater than 0, else input plus 0.3. So yeah, this is in fact, this is the method of gradient descent. So what I'm simply doing is that I'm simply putting an if-else condition that says that simply travel in a particular direction. Simply travel in the opposite direction of gradients if you want to reach to the mean. That's what I'm doing. So I'm simply doing that, and this will evolve into my gradient descent equation. All right. So and I'm going to do square I fry z. And say, and I'm going to be plotting my point again, right? So it's going to be, I'm just going to copy some stuff from the top. It's the same stuff, right? So initially I was at 4.016, and now I'm at 3.7 and 13. And let me run this code again. And if you want to run the same code again and again, you simply do CTRL plus enter, CTRL plus enter. Shift plus enter to run the code and come to the next line of code. CTRL plus enter if you want to stay in that cell and run it again. So 3.4 now. 3.1 now. So if you look at slowly coming to the minimum, and you'll see at one point when it shoots to the other side, it will come back again. So that's what I'm trying to do. So this was my gradient descent equation for now. And we're going to make it much more efficient. All right, 0.7, 0.4, 0.1, it shoots to the other side, which is now minus 0.2 and then 0.0. And so now the gradient is in the opposite direction. So now it has to shoot back in the other direction. So now you look at it, it's gravitating towards the middle. So now I've come to the minima, and if I run it again and again, it will stay close to the minimum. That's the beauty of gradient descent. All right, are you guys following me? Very important concept, gradient descent. All right. All right. Now let me make this slightly more efficient, because if else conditions don't work well when you want to run like very huge models. Anyways, um, when you're at 4,16 and the gradient is, let's say, um, let's say 8 at that point, it simply means that the rate of increase is so large, you can actually make it slightly more efficient, and you can say that, well, okay, so when you write this, right, so I'm just going to be copying this entire thing. I'm going to initialize this. I'm going to initialize input as 4 again, because now input is some 0.1. Instead of this, I can simply remove this and say that I'm going to do input minus gradient of square input, right? Because this is also the same thing. So whatever is the value, you just go that much in the opposite direction. But then gradient, like -8 would be too large of a jump. I don't exactly want that, so I'm gonna reduce it down by a small factor. I'm gonna say, let's say 0.1, and so 4 now 8 will become minus 0.8, and then 4 will become 0.4 and stuff like that. Now let's run this again and let's see what happens. So initially I was at 4. Okay, sorry. Let me initialize this, and let's run this. I'm at 4. Let me run this again. Now I'll be at 3.2. I've taken quite a large jump. I've taken a jump of 0.8 for now. Slowly it will start reducing. It becomes 2.6, which is a jump of 0.6. 2.0, 0.6 again. 1.6. 1.3. 1.0. So I'm coming to the minima. Oh, sorry. Where did I do? Uh, 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 So I think I need to. Let me. Let me run this again. So 2.6, 2.0, 1.6, 1.3, 1.0, 0.8. Now you see we're taking smaller and smaller jumps because the gradient value is reduced, which is actually works pretty good for us, because when we were farther away, we would like to take bigger jumps. Now we're at the very minima, so you would like to take very small jumps in order to optimize that thing to the very last point. Because in the previous case, when we were taking constant jumps, you would see that we were jumping between 0.1 and minus 0.2, constantly jumping between these two values. So uh, now the only way to actually break out of this circle is to reduce that small step size. So from 0.2 you go to, let's say, so minus 0.2 you go to minus 0.05, and then you reduce it further and further. So that's the way to go. If I run this again, 0.4, 0.3. So now I'm coming to the minimum, and finally I've come to So why exactly did I use this gradient descent so uh, like so? Why did I even talk about this? Like, how is it even related to, let's say, my linear models? And I'll tell you why. So deep learning, machine learning, the guys in research found out a very good way to use gradient descent in order to find that WX. Now, if you think about this model that we've built over here, you see, what's the mathematical definition of fitting this line through this data well? Like, I can describe it in words like fitting well. Like, how do you define it mathematically? The way you define it mathematically is through something that is known as a loss function, which is nothing but like how far away is your model from the actual data points, and you want to minimize that difference. For example, let's say the price over here is around 600, but my model predicts, let's say, 550. In a scenario when that model is probably not the best, and let's say the model, I initialize it as a flat line, horizontal line, let's say, right? The difference between 600 and the corresponding value of that model at that particular X will be very large. And your task is to minimize that in the best possible manner. Of course, you can't bring it to zero all the times, because I mean, like, you can't, like, in order to bring it to zero, you will have to make this line coincide with all of these points, which is simply not possible, because this is not because you're trying to fit a complex curve using a simple linear model, so you can't fit all the data points. But we want to do it in the best possible way, and so we want to minimize this loss or this error between the predicted value and the actual value. And here is where gradient descent comes into. All right. So you must have seen sort of. Okay, so I'll define it mathematically. What I'm trying to do. Here is the loss function that I was talking about. So for all the data points, which is 1762 data points, whatever was the actual y and whatever was the predicted by my linear model y is equal to wx plus 3 for a given w and b, what is the difference between them? And so there can be two cases in which, and then you sum up all the values. But since this difference can be positive and negative, I don't want them to cancel each other out, because I mean, like, for me, as far as I know, a line going above the actual data point value versus it going below the actual values is as bad as the other. Like, it's not that one is good, one is better than the other. So why should one should have a positive value, one should have a negative value? So for that, I just simply square them out. So it's gonna simply make it a positive value. Now you can simply remove this square and do an if-else condition that says that if pred is greater than y, just in a way, so you simply do an if-else condition that says that what should come first, what should be subtracted from what. But square is a very convenient way to do that. It's also very easy for the computer to, just because it becomes uniform at that point. If-else conditions has some, it's a break in the computational graph. That's it.
So why not absolute value?
Use it. Doesn't matter.
Okay.
But the thing with square is that, so absolute value will work, right? But people figured out that the more the error, so the more the difference between the model and the predicted value, it becomes progressively worse. So you want to penalize, so you want to like give an error. This is actually an error, right? And you want to minimize this error. So as the difference starts between predicted value and the actual value becomes more and more, it becomes so you should ideally penalize this model more and more. And the square value does this very well, and the square function.
So I mean, any other power would, I guess, also work better for this case, right? Penalizing. So raised to 4 would penalize even
Yeah,
more.
yeah.
Okay.
But power 4 becomes, I mean, square does the job,
Yeah.
to be honest.
Okay.
Yeah.
Yes, got it.
Now, absolute doesn't actually penalize it as well, because it penalizes. So it will penalize a difference of 50 as equally as a difference of 500, which is, so it's just an optimization technique. That's all.
Yes, sir, I got it.
And now, since you're summing them, all of them up, mathematicians also, so they put this 1 by n, which is an average across all the values. This is just something that mathematicians said. It doesn't. There's no such there's no such difference as such, except for one very small thing, which I think you guys should not care about, which is precision within the CPU itself. But then I've usually seen that it helps. But ideally, like in theory, it doesn't matter if you put this 1 by n or not. But we still do. I mean, like, because why not? Because mathematicians, because otherwise you'll just become confused. Otherwise, between all these theories, in most books you'll find this 1 by n. In theory, you don't need this 1 by n. But in practice, I've seen this 1 by n works better because of precision. Okay. So here's what I'm going to do. Here's how my predictive modeling is going to work. Step 1, initialize your W and B to some random values. Step 2 would be, I'm going to be running this. So do you know like how I pressed enter again and again? So gradient descent is not something that just gives you an answer at once. It's an iterative mechanism, in the sense that you need to run this again and again for a particular number of times in order to come to the optimal value. And that you get to decide how many times you want that. It so happens that like you'll find that in deep learning, certain number of values are sufficient to do that. And whenever you run beyond that certain value, it'll not give any particular effect. Like, because if you notice, like at the end, once it reached 0.2, the difference becomes so small, the gradients become so small that the optimization becomes so slow that you're simply like, okay, fine, this is a good optimal value. I don't want in theory, you can go infinite number of iterations, but you don't want to go infinite number of iterations because you have limited computational resources. So for each iteration, I'm going to be calculate the gradient and go in the opposite. Go in the direction opposite to the gradient. By the way, this line over here, this is called the gradient descent equation. And let me. So this is exactly the gradient descent equation. This 0.1 over here, it's called the learning rate. So we're going to be abbreviating it as LR, or learning rate. In some courses, you'll find this as alpha. In some cases, you'll find neta. And it doesn't matter. Like so, all these things only come in academia, because since they're teaching academic courses, they have to use Greek alphabets. But we are practitioners and we don't care about those symbols, so we're going to just kind of make our lives easier for ourselves. And we're going to use a small symbol that is known as LR. It's called learning rate. So this thing over here is known as the learning rate, and 0.1 is a very standard value. Sorry, 0.01 is a very standard value within deep learning, but for now we have a very small model. 0.1 works. I'm going to be using PyTorch throughout this lab sessions, because I personally feel that it's an easier learning curve, and especially and it's very easy. And personally, I feel that PyTorch is going to take over all sorts of deep learning avenues, including industry and academia in the coming few years. In academia, PyTorch is already very prevalent. Like no one uses TensorFlow anymore. In the industry, TensorFlow is still used, but I personally feel that TensorFlow is going to be replaced by PyTorch very soon. It's much more dynamic. It's much more smoother. I'm a huge fan of PyTorch. But that being said, I can guarantee you that learning one doesn't necessarily mean that you cannot learn the other, in the sense that given PyTorch is nothing but a tool. I mean, it's not that you learn or unlearn it. So, and tools are something that you acquire as per your needs. Whenever you need TensorFlow, you're just gonna go to the documentations and you're gonna look at how you're gonna do it, and you can simply learn how to do it. Right? It's not that it's a skill. It's a tool, and so tools. Think of tools as something that you can use and dispose whenever you need. Right? Think of PyTorch in the same way as well, in the sense that don't memorize anything, but whatever you need, go to the documentations or go online, see whatever you want to do, and use it as per your need. Anyways, I'm going to be initialize two random variables, that is W and B. And so what requires grad does is that it tells PyTorch that these two are not any variables. These two are variables corresponding to that they're going to have gradients corresponding to them, and you're going to take gradients with respect to them. By the way, we don't calculate gradients by hand anymore. So technology has come far ahead, and PyTorch can actually internally calculate the gradients for you, whatever calculation you do, without you telling them like what equations you've worked on. And we're going to learn about how this happens in the later lab session. But you don't need to calculate gradients by hand. Now, I calculated gradients by hand over here because it's a very simple example, and then I didn't want to write all that code. But you're going to be looking at like very deep learning, like very huge deep learning models in the future, and you're not going to calculate gradients by hand because it's boring. It's useless because computers are going to do it for you. Why do you want to calculate them by hand? That's a simple logic. So I'm just going to tell them that just keep track of the gradients for these two parameters. And let's say let's look at like what these parameters are initially. It's taking some time because I'm importing a very huge library, which is PyTorch. Right. So initially my W is 1.53, and initially my bias is 0.63. These are random values; they don't mean anything. Now, if I were to plot them over here, you would see that it's a totally bullshit line. Like, I mean, it doesn't make any sense. So it's just random. Now, when you calculate this, when you calculate this error, which I've written over here, which is 1 by n squared minus y, it will be a very, very huge value. And you want to minimize that using gradient descent. All right. In PyTorch, we don't use lists anymore. We use a thing known as a tensor, which is very close to what a list is, but it's optimized for deep learning calculations in the sense that you can feed it inside a GPU very efficiently, and so PyTorch expects everything to be a tensor. Rule of thumb. So I'm going to be creating my tensors out of the lists that I have, and I'm going to convert them into floats. By default, they're going to be int 32. So by default, because my days were like simply 1, 2, 3, like integers. I want to convert them into float because because otherwise gradients, because there's going to be a discontinuity in the gradient descent. Like gradient descent only works in smooth functions. In smooth functions, you can create with integers because integers are discrete values. Just some basic mathematical concept. It works very similar to a NumPy array if you guys are familiar with that. Tensor.shape. Let's give it a shape. So I have 1762, 1762. All right. I'm going to create a model which is nothing but x and parameters w comma b is equal to params return w times x plus b. Now this is a very inefficient way to calculate products and sums, as you'll see later on. But then for now, because we have just one variable, it works fine. So I'm just passing, let's say, now here's the beauty about PyTorch. You can pass in the entire tensor, which is all 1762 values, and it's going to calculate all of them simultaneously and return all of the values simultaneously as another tensor. So that's what I'm doing. I'm passing the entire extensor value through my models. Now, if you remember, initially I had to like sort of do a list comprehension, which was, I'm like, look at this. I had to run a separate for loop to do that. Now, for loop is a very inefficient way to do that. It has a very high time complexity. PyTorch, now tensors are actually optimized to do all these calculations within the GPU. So these are called CUDA calculations. CUDA is nothing but the library that runs deep learning libraries on GPUs and even CPUs. So it's optimized for that process, and it's a very interesting thing if you want to go into that stuff, but you don't need it for now. So my let's look at like one prediction, let's say, for example. And so there is 0.63 and 0.63 is the loss corresponding to that. Now, I'm going to be defining my loss function, but I'm not going to write it from scratch, this one, because PyTorch already does that for me. Now, this loss function in statistical theory is known as mean square error loss. Mean square error loss, or MSE loss for sure. Now, PyTorch implements this for us, so I don't need to do that. So what I'm going to do is that loss function is equal to torch.nn. .nn is actually the submodule within PyTorch which contains everything related to neural networks. It so happens that mean square error loss is it will be used very much in what do you call your deep learning calculations. So it lies under that. F loss linear regression. I'm going to take in a prediction. I'm going to take in a target because that's what's my question. So it's a function of prediction and wise themselves. First of all, I'm going to make sure that these two are of the same size, because otherwise it's going to return me an error. Because otherwise the calculation can't happen. And assert is a good way to to identify like what exactly is the issue. Like instead of going through the entire error stack, you can just simply just by inserting this one small line, you know that this exactly was the error and that is why the code stopped at this. Assert, if you guys don't know, is a keyword in Python which takes in a true or false condition. Now, if this condition is true, it does absolutely nothing. Like it just runs the code without doing anything, without printing anything, without doing anything. But in case this condition is false, it will stop exactly at this and it will throw an error. And so when the model throws an error, I will see that it stopped at this assert line, which means that this error was false. So I exactly know what is the issue with the problem with the model. That's how it works. So I'm just going to do loss function. I'm just going to pass in the prediction. So PyTorch does it for me. Anyways, here's an exercise for you guys. I want you guys to implement this mean square error from scratch. So that's one exercise for you. I'm just going to write it over here. It's a good exercise. Based on your expertise, it'll take you about, let's say, an hour maybe, but it'll be a good exercise. Implement MSE loss from scratch. All right. I'm gonna do. Let's calculate the loss regression. It's gonna take my threads, which I've calculated here, and it's gonna take my y tensor, which is nothing but the ground truth. Let's look at the loss. So it's a huge loss. It's 3 million or so. All right, never mind. And now that's step number 1. We calculated the loss. Now step number 2. Okay, so before calculating the gradient, you first calculate the loss. And now since you want to minimize the loss, you take gradients. So okay, let's look at this. In this graph, we were trying to minimize the value of y, and we were changing x accordingly. So x is the independent variable, and we were changing y, and our task was to minimize y. In order to minimize y, we had to take the gradient of y with respect to whatever independent variable we have. Over here, the independent variable, like, so whatever we're trying to adjust, now we can't adjust x and we can adjust y because that's the data that we have. You can't change that. Only thing that you can change, so independent variable over here in this case would be w. Your task, and you want to minimize loss, so you take the derivative of the loss with respect to w. And so that is why we mentioned that these are variables that have gradients like related to them, and so keep track of all these gradients. If you want to calculate the gradient, all you have to do is type loss dot backward, right? Press, and now let's actually look at params. Param 0. Now all of these actually have another attribute, which is grad, and you look. Okay, never mind. Okay, let me. Now look at this. The model, when I do params.grad, it automatically returns the gradient of w and b correspondingly. And now I didn't have to do anything else. So that's how efficient that is. Anyways, I'm gonna be now I'm gonna be doing that loop, which is learning rate. I'm gonna set my learning rate, and it's something that you set on yourself. So LR is equal to 1 in neg 4, which is 10 to the power minus 4 as of now. Params.data, and I'm doing this initially because the gradient value is so high that I need to, I need to compensate it with a very small value of learning rate. Params.data, which is nothing but the actual value of the parameters WNB, is minus is equal to LR times params.grad. I'm going to do a params after that. Let's see. Yeah, so that is one side. So I'm going to be writing the code for, let's say, one particular cycle. So here's the code for one complete cycle, all right? And so I'm going to reinitialize my parameters. Here I'm going to initialize them as not random values but zeros, let's say, because otherwise they gave me a huge problem because values explode at that point. And so on and so forth. But we look at better ways to initialize our variables when we go further into our lectures. Requires grad. I'm going to do def train one iteration. It's going to take in params. It's going to take in learning rate, which is by default 1 in neg4, which is 10 to the power minus 4. Preds is equal to more. So here's step number 1. Find the predictions, x tensor, params. Step number 2 is calculate the loss, which is loss linear regression. Preds, y tensor, calculate the gradients, loss dot backward. right? And gradient descent equation. So let me write this over here. Step 1, calculate predictions. And this is the entire pipeline of a deep learning / linear model. And you look at this iteration again and again throughout. Very important, these steps. So when you're revising this, I want you to revise specifically the process that we're going through, the exact steps that we need. Very important. Calculate loss between spreads and actual wise, right? Calculate gradients and update variables through the gradient descent equation. So params.data minus is equal to LR times params.grad, or params.grad.data also works. So the value of the gradient itself. Finally, you need to do one thing, which is you have to reinitialize. After reinitialize, you have to make sure that the gradient values are none or 0. The reason that is because by default, whenever you're doing this loss dot backward, PyTorch by default will keep on adding the gradient value to the previous gradient value itself. So it will keep on adding by default, and this is quite useful when you handle very large deep learning models, or very large data, not models. It's very useful in that case, and we look at that. And so, in case, because in each iteration we want a fresh calculation of the gradients, and so we'll have to initialize this to none or 0 each time. So 0 plus current value is the same as current value, or if you initialize it as none, it will by default be initialized as current value. So either one that works. That's one iteration. All right, I'm gonna let's do some initial stuff. So I'm gonna be plotting my linear regression model. And I think we'll stop after this thing. I wanted to cover classifiers as well, but we'll look at it in the next lab session. Probably spend only about 20 minutes or so, because it's a very similar concepts are not very far off concept. In fact, almost the similar, and you'll realize that the only difference between linear regression and linear classification is how we design this loss function. That's it. Everything remains the same. We'll talk about the difference. plt.plot x tensor y tensor, right? Spread is equal to model x tensor params dot detach. Okay, take my word for it. Dot detach is very important. The reason it is important is because how do you think that the PyTorch can calculate gradients without you ever telling them like what steps you've taken? Like, so over here we took an x, we passed it through a square function, and according to whatever function we passed it through, you calculated the gradients. Now let's say you pass it through another equation, that is x squared, and then you pass it through summation, and then you did another square. Calculation of gradients changes according, chain rule, if you guys remember from 11th or 12th standard. The reason PyTorch can keep track of the gradients is because when we told PyTorch to take care of the gradients over here, dot requires grad, what PyTorch does is it keeps a track of all the operations you do on W and B. So when you do this, PyTorch will keep it in, will store that will actually remember that you've done this operation, and whatever operations you've done, it will use the chain rule to go back to all those steps that you've taken, and it will and it will calculate the gradient accordingly. Now over here, I'm just simply plotting my value, and I don't want and I'm passing my x through my model, so there will be some computation. I don't want my model to keep track of this because it will affect my gradient descent equation. Do you get it? Do you get it? Now, not very important as of now. You'll understand it slowly, but just know that detach is very important, because otherwise this line will affect my gradient descent. Yeah, I'm gonna plot this. So X tensor and prediction. Right. I'm gonna print MSE loss linear regression red and white tensor dot. Let's look at like the initial stuff. So look at this. So I initialize my W and B as 0, which is why this is how the model looks as of now. And now let me run this for, let's say, 50 iterations, okay, like, which is very reasonable, I'd say, because it's a very small model. So for 50 iterations, I'm going to run that iteration, which is going to take in the param. Learning rate is, let's say, so I've seen this work before. 2 in x7 works, which is 2 to the power of -7. And once I'm done with that, I'm just simply gonna plot model perhaps. Now look at this. My gradient descent has slowly come to the optimal value as well. And so now you guys have officially trained a linear regression model from scratch using, everything from scratch, including the data, including. So that's how much, that's what I'm trying to give through this practical course, which is everything apart from the theory courses. How do you practically build your models from scratch? If you were to train this once again, so I'm just going to run this again, you would see that now I've reached that point where I can't go any further. Like I can't get much better results. Of course, there will be some difference, but I would expect it not too much. Yeah, it's pretty much the same, because I've now reached to the minima, pretty much the minima of that this curve over here, or whatever curve that loss function would be forming. So in my case, the y would be the loss function and the x would be w and b. So it would in fact be a three-dimensional curve, if you think about it, in which the two dimensions which are independent would be w and b, and there would be, let's say, like a curve related to a 2D curve related to the loss function. All right, that's about that. And now, since I've calculated this, let's you can again, once I've calculated this, you can calculate, let's say, the stock price in 2018, or like some random date that you want to work in. So you've now built a linear classifier model. I think I'll stop at this point, and we'll look at logistic regression in the other class. But before that, I want to talk about one more thing, which is deployment. Which is, once I build this linear classification model, how do I how do I build it? How do I build an app that tells me for it? And so for that, I'm going to be using this very cool app that I came across a few months ago, which is known as Gradio.app, which is the fastest way to demo your machine learning model with a friendly web interface, so that then you can use it anywhere. So for that, I'm just simply going to do import. So I think Gradio won't be installed in the Google Colab, so I'll have to first install. So for that, I'm just simply going to do pip install Gradio, right? with an exclamation mark, of course, because it's a Linux, because you install through the Linux shell. After that, I'm just gonna do import. So I'm just look. I don't know how to. I don't know how this works. So I'm just looking at the documentation. It says import Gradio as gr. All right, I'm just gonna do that. All right, and just give me a second. All right, so I'm gonna use this, but I think this is corresponding to the MNIST sort of task in which I can. Who wants to play Pictionary? Okay, so I can draw one of these two things. So let me draw, let's say, a tooth. Yeah, it shows that it's a tooth. All right, and then let's say, what else can I? Laptop. Okay, let's draw a laptop. Yeah, it shows that it's a laptop. All right, so I can actually deploy. So someone must have built this model, but like on Python, like on the Jupyter notebook that the Collab notebook, it's just going to be some lines of code. It's not going to be as interactive as this. Gradio.app is giving me a platform in which I can build such interactive apps, and I can share it with anyone. So you guys have just built, let's say, a stock prediction model. Let me run this. All right, so I'm just going to do a Gradio.interface. But I probably have to change a few things, and I'm trying to figure out, like, inputs is equal to sketchpad. So I'm not using a sketchpad. Input is going to be actually a number, and if you want to, like, you'll have to go through the documentation if you want to understand, like, how do you want to navigate through this. So text box number, so my input component will be a number. String shortcuts is equal to number, and my output will also be a number, actually. And function is actually the model, so function is not going to be. So I'm going to actually have to write a def predict. Let's say it's going to take in a date. Right? I'm going to return model date. But I mean, model returns a tensor, and I specifically want the number component if I don't want the tensor itself. So dot item will do that for me. But here's another error. So date will have to first be converted into date time object, right? So what's the format of the date I was trying to look for? By the way, guys, if you think that I know any of this by heart, I don't. I'm learning with you guys as well. But the only thing that I can give you from these lab sessions is, like, how do you actually go about solving a problem? Your best friend is not going to be me. It's probably going to be Google search and the documentations or whatever, and Stack Overflow and stuff like that. So stuff like that, right? And trial and experimentation. Trial and error is the best way to learn when it comes to practical stuff. I guess you guys already know that. But anyways, the date will look something like this. So I'll have to first split it. I'll have to first process it because I just want the date part of it, right? So I'm going to have to remove this time stuff. Actually, never mind. We'll just make it easy, and we'll make sure that we pass in. we make sure that we pass in very specific stuff. But I'm wondering, like, how do we actually pass in the data to the model? Just give me a second. Yep. This. Right. And all right. Yeah, I think this should work. Let's see. Oh, sorry. This will be predict. So I have a link now. Let me go to that link. And let me share that link over here as well, so you guys can look at it for yourself. And I mean, you guys must have built it on your own as well. But here you go. Now I have this interface in which I can pass in. Oh, sure. There's an error. Okay. Predict expects me to give a single input. All right, I'll pass it as a list of values. Date. This. I think this works now. I'm just going to pass in, let's say, 2018 1231 as a list. Well, it doesn't let me. Oh. Okay. What about I directly pass in the number of days that I've passed, because input has to be a number, right? So, anyways.
So you can take the input as a string and then pass that string into
Yeah,
predict.
you'll have to do all that stuff, but just for lack of time, I'm not doing it as well. Like, yeah, you guys should do it, by the way. Like, it's a very good exercise, I guess. Like, yeah, so the way I would do it, that I was taking a string, then I would break it down, and then I would convert them into integers and then pass them directly through this function, which is calculate distance. But let's say how many days. So I think we calculated that today. So today is around 4. I think this is the number. So I think 22nd January 2022 is that many days since. The output is negative. Just a second. So if I do model 4431, I get a negative value. Oh yeah, I do get a negative value. So I must have 4431. Okay. Anyways, here is how you deploy your models, and we look at. I don't know why this is coming. I think this worked fine till now, but I don't know what happened. Never mind. So this is how you deploy your models, and then this link that you'll have, you can probably share it with your friends as well, right? Google stock on the crash. Anyways, no, we must have done some error somewhere. But anyways, doesn't matter. I think we're pretty done with that. So next class we'll actually start with linear regressions, and then we'll start with neural networks and how you extend that linear classifier, a linear model, into a neural network, a linear model into a neural network model, and then from there we'll solve much more interesting problems and we'll learn a lot of stuff. So that's all from my side today. Thank you guys, and see you guys next Saturday. If you have any questions, I'll stay here for some more.
One question. In
Sure.
the graph that you made, the last one, like the one which you made, the training one,
Yeah.
the intercept value was still 0, so well, it's seeming like it should not be.
Is it? Why? No, it's not. So I
This one,
think.
yeah. Are we allowing it to
Oh,
change,
it
or
is. Okay. No, I mean.
maybe we're not allowing it to change? That's why it's...
So yeah, I mean, you probably the reason why this happens is because the gradient of so this is a problem with very small models, and when you run gradient descent, uh, W's gradient is related to X, which is dynamically changing, and so W gets trained very easily. But then the gradient of B is constant multiplied by whatever. How do you calculate? Let's say when your y is equal to x plus b, uh, the gradient of b, for example, with respect to the loss function would be this minus prediction whole square. So it would be related to y itself, 2 times the value of the loss function itself. And so at that point, let me think about this. But one explanation is that it's simply what result did we get? No, actually, we did get a good result in the previous case. It simply is a characteristic of this gradient descent. Like just this particular problem itself, that gradient descent can't get out of that B0 space. In which case, we can't do pretty much.
No,
But I'm wondering why this happens.
somewhere I've seen that they purposely initialize it randomly so that it doesn't fall in this loop of...
So let's actually try that. It'll take just 2 minutes. Let's say my parameters over here are not zeros, right? And let me initialize them to some random value. Yeah, I think that's the issue. I think you're right. Because a 0 multiplied by anything would give you a 0 value. Now it doesn't matter for what do you call W, because W's gradients are also affected by that X, which is dynamically changing and it's non-zero. But wherever I initialized my W's and the D's, oh here, no, this is not the case. Yeah, here. Let's see. Nope. Yeah, what if I put it, let's say 1? Yeah, okay, there is still an error. What about, let's say, oh, there is an error. we never ran this. And let's say it's 100. Oh, yeah, so it is definitely changing, but it's still stuck at that particular value, and I'm not sure why. All right, let me think over this and I'll get back to you. I don't know. So there's nothing wrong in a gradient. So it's definitely because of the mechanism of gradient descent itself. But I probably never thought about like why exactly this is happening. So I'll probably think about this.
Okay. Thank you.
If you get an answer, please tell me.
Thank you.
All right.
So, what is the function of that dot detach method that you used?
Yeah, sure. By the way, you guys can call me Palash. Dot detach. Dot detach is a way to tell PyTorch that whatever you do with this equation over here, don't consider this while calculating your gradients. All right. So why you want that is because otherwise, whenever you do any sort of operation, now you're not telling PyTorch how to calculate the gradients, and the way PyTorch calculate gradients is that it keeps track of all the operations that you've done on your equations. Now you want to do now you want to include those operations in your gradient calculations which contribute towards this training cycle, right? This over here is not part of the training cycle. It's completely outside of that. I'm just plotting them. I don't want it to be included in my gradient calculation steps. So I have to tell PyTorch that don't consider this operation. Otherwise, it will keep track of this. And when I'll do this backward the next time, it will like include this operation too in the gradient calculation, and it will take a derivative with respect to that, and that will completely mess up my training cycle. That is why. Like, do you get it?
Yes, yes.
All right. So if there are no other doubts, I'll probably close this lab session. Thank you all, and let's meet next Saturday.